So we're going to evaluate the thermal stress in this unconstrained bar. So in this instance, we have a 20-meter section of a rail track that is laid in ambient temperature at 5 degrees Celsius. And it's then exposed to some elevated temperature, 50 degrees Celsius. And we need to figure out how much this thing has expanded. So of course, we have to use our coefficient of thermal expansion, and we have that right here. So that's our rate of change per degree Celsius in the bar, and we need to figure out what the change in length is. Now, in terms of the principle, let's use this diagram to ensure that you understand what we're going to do. So T1 is representing when the track was cold, so that's at our 5 degrees Celsius. And that capital L is representing the length of the track at that point. And that's our 20 meters. Now, the change happened in temperature, and the temperature then rise to 50 degrees Celsius. So that's right there, T2. So that's a change in temperature, and that results in a change in length right there. So our objective is to figure out what that change in length is. So let's do that. So to do so, we have this formula that we'll use for change in length, and that equals to our coefficient of thermal expansion times our original length and times that by our change in temperature. Now, of course, our change in temperature, let's just ensure that we understand what that looks like. So that's just going to be our final temperature, take away our initial temperature. And it's very important to know that that could be from a hot to a cold or from a cold to a hot. It just means instead of expansion, we could have contraction. So let's get into the calculation. But just before we do that, I am really passionate, guys, about growing this channel, and that's why I upload at least 5 videos per week, Monday to Friday. And I would really love to get your support by just subscribing to the channel and give this video a thumbs up. And if you don't mind letting me know exactly where you're studying from and at what stage in your studies you are at this point, I would really appreciate the engagement. So let's get back to the calculations. So for our change in length, what we have the coefficient of thermal expansion, and that's our 12 times 10 to the power of -6. We also know what our original length is, and that's representing our 20 millimeters. And then now for our change in temperature, that's going to be 50 for the final temperature. Take away our 5 degrees there for the initial temperature, 5 degrees Celsius. So what we're left with then is 0.0108 meters. So that's representing the change in length, and that's that little bit right there at the very end, the extension. Now, what we are going to do next is to analyze a system where the bars are actually constrained, and that one is a little bit more challenging than this. But to check that out in a very easy step-by-step method, watch this next video right here.